Before I start, I'd like a question for the audience, show of hands. How many of you are here for the first time? We weren't here. It's a pretty decent show of hands, actually. And of you, how many of you have taken a class on machine learning or anything related to machine learning? Almost none of you. That's actually good in a way. This presentation I'm giving is a continuation of a presentation that I gave last year, which was on the applications of machine learning to cybersecurity. And because I recognize that many of you don't have a background in machine learning, and this is a topic that kind of requires an understanding of both, I do have a few slides to provide a sort of review of the presentation that you had been unable to obtain. And to start, I'd like to give a brief description of machine learning. So what is machine learning, right? Well, an informal description that I like to give for it is that machine learning is a collection of techniques that enable a machine to learn the definition of a function. So you can think of a mathematical function that is some mapping from some set to another set. And in this case, that input set is going to be feature vectors, and that output set is going to depend upon what type of machine learning application we're dealing with. In machine learning, we have a few different approaches. One of these is supervised machine learning. So in supervised, the data we're trying to learn about has labels, usually some sort of a class. So imagine you might have a picture of images of different things, and we're trying to find all the fire hydrants. And so this might be labeled as an image of a fire hydrant, or this might be labeled as an image of a stop sign, and so on, right? We have different labels describing what those images are for. And so that's supervised machine learning. We're mapping from the image or whatever feature vector we have to the labels. We also have unsupervised machine learning, which means we don't have labels, but what kind of output is going to be based on how many classes we think we have. So in this case, say we know that we've conducted a bunch of cyber attacks on some machine, and we want to classify these into different cyber attack categories. So say we know we have 5 different types of data here, 1 benign and 4 different attacks. And we're going to just sort of group these together and make 5 different groups. And then we can apply labels to those groups later on. Finally, we have reinforcement learning, which is a sort of specialization of machine learning towards planning. So we're trying to learn some sort of a policy for an intelligent agent or AI to act upon. And that is based upon a sort of reward program to refine that policy. That's reinforcement learning. Now, machine learning has 2 main types of tasks that we work with, one of which is classification. And so that is where we are trying to figure out what group something belongs to. A lot of what I provided for the supervised learning was supervised classification. So we're trying to figure out whether something is a fire hydrant or a stop sign or whatnot. But we also have regression, which is where we're trying to learn a more pure arithmetic function. So we're trying to create some real value number as our output instead of a label. So how in the world does machine learning relate to cybersecurity? Well, we have a few applications of them that I discussed in the previous talk. And these are intrusion detection systems, incident response, and automated red teaming. So intrusion detection systems are one of these applications I think deserves a lot more focus. These are programs that can monitor all of the activity on some computer or a network and try and figure out, based on all the data that it's collecting, when an intrusion has occurred and raise an alarm if that happens. We also have incident response. So we've got our alarm, but now what do we do about it? So we can input a series of security alerts and background context information, and we try and figure out what's the appropriate response to that threat. So are we going to shut down some network connection or to stop a adversary, or are we going to just block an IP or whatnot? Finally, we have automated red teaming, which is based on, well, let's test the strength of our cyber defenses. You're going to use something like reinforcement learning to plan out an attack against some system and figure out where the weaknesses lie in our defenses. Of these applications, I'm going to go a little bit more in depth on one of them, and that's intrusion detection systems, because I think they are going to be a bit more of the future of machine learning or cybersecurity. So I say future, but actually these things have been around since, I want to say, late 80s, early 90s. That's when the first intrusion detection systems came about. And so because of that, we've got a lot of different approaches to them already. We have, first off, host-based versus network-based intrusion detection systems. So we have completely different focuses. One is we're trying to stop attacks on one specific computer, and we're dealing with all of the events that happen on just that machine. And the other is we're trying to stop attacks going across some sort of a corporate network and whatnot, and trying to detect attacks going between machines. We also have signature-based versus anomaly-based. So signature-based is saying we have a bunch of examples of what an attack looks like, and we want to find anytime something looks like these. And so anytime you work with a virus scanner, where it's got some list of definitions and it's going to go scan all of the files on your system and say, hey, does this look like any virus I've ever seen before? That's signature-based intrusion detection in a way. Anomaly-based is kind of the opposite. We don't work with what does an attack look like. We work with what does normal look like. And then we raise an alarm when anything deviates too much from normal. And we can refine that with sort of a rule-based system where we have a list of rules of what normal should look like, and we have a statistical approach where we just look at all the data and say, yeah, this is X% different from what normal should look like. And here's the thing, though, regardless of what approach we're using, all IDSs require a lot of data, good data. For host-based systems, that is going to look like some sort of capture of system calls. We're going to look at when processes are created or destroyed, when drivers are loaded or unloaded, when the file system is written to, how much is written, when it's written, etc. Whereas network-based intrusion detection systems are going to be looking at captures of network traffic. So that could be as fine-grained as something like packet captures. So we can look at every single individual byte that's being sent from one machine to another, or we can look at a broad overview like NetFlow, which is going to tell you, okay, this IP sent this many packets and this many bytes at this time to this other IP using these ports. That's a sort of summary information. And one big thing, though, is that if we want to do any of this with some sort of a cyber attack, right? Say we want to teach it what's the difference between a cyber attack and its normal behavior, then you need labels. And labels are the pain in the butt that makes everything with IDS difficult to research. IDSs do not have a lot of good publicly available data sets. And that's kind of due to the difficulty of generating all of the labels for things. So if you were to, say, capture all of the traffic that occurs on a machine in one day, right? Then conduct a bunch of attacks on them. Those are going to be interspersed with your normal behavior, and you need someone to look at the NetFlow logs in some Excel sheet and painstakingly write, okay, this was part of an attack, but this one was normal, and this was part of a different attack, and these next 5 are normal, etc. It is extremely laborious, which is why we don't have that many data sets, and many of them are old, and also many of them are very, very unbalanced. So you might have like 95 or 98% of the data being benign traffic and 2 or 5% of it being attacks. And that's going to lead to some problems later on. There's also some issues with, I'll get you with it, pre-processing. So all of the data that machine learning programs like to work with are feature vectors. So like think an array of floating point numbers. But all of the data that we're collecting is usually categorical, like an IP address, a port, or something like that. Yes, you had a question.
You mentioned it was difficulty in finding public data sets. Like companies tend to have their own private data sets that they kind of hold on to, like Microsoft and ours runs on.
Yes, some companies will do that, but keep in mind if you have every single company that wants to work on an intrusion detection system has to generate their own data set, that's going to become very expensive. And what's also kind of sad is the best data would be, you know, an evidence of an actual cyber attack out in the wild, and nobody wants to give away that data because it would lead to a lot of embarrassment for that company. Any other questions before I continue? No? Okay. Other problems with intrusion detection systems are false positives. Say you have a classifier with a 1% false positive rate. In terms of machine learning, that's actually not that bad. But think about how frequently a real computer system is under a cyber attack. Like how much of its traffic is due to outside actors. Not that regular, probably less than 1%. A little application of Bayes' rule is going to tell you that that's going to mean that the majority of your alarms are going to be false alarms. So it's not that great. And when you get too many of these, you're going to get people to stop using the IDS, which means it's no longer going to be helpful to us. Finally, we have zero-day attacks. If you are using a signature-based intrusion detection system, you have basically no defense against zero-day attacks. You have never seen something before, it is not in your signature database. Anomaly-based intrusion detection systems are kind of designed for this, but they're still imperfect. Also, if we have an attacker that can somehow access our model, they can craft an attack that is specifically designed to evade detection. So that's IDSs. This is where generative machine learning comes into all of this. The big problem I'd mentioned was, well, we don't have good data. So what's the solution? Make more and better data. We can train a generative model on some data set that is a bit smaller. We have our 5% attacks. We can learn a statistical distribution of that data set. And what our generative model can do is it can take random noise, say an input from like the dev random on your Linux machine, and we can turn that into more data that is within that same statistical distribution. You can think of it like a classification task in reverse. Instead of inputting a feature vector and getting a class, we are instead inputting a class label and getting a feature vector out in response. So I'm going to be talking first about 4 different types of generative machine learning algorithms. All 4 of these are very recent, starting with generative adversarial networks, or GANs, and variational autoencoders, or VAEs. These both came out around 2013 or 2014. Before these 2 came out, generative machine learning was sort of stuck in a rut. There were not a lot of good algorithms. They had to deal with a lot of very impractical problems. Basically, we couldn't generate really good data without spending an exorbitant amount of time. The other 2 are even more recent than that. And when I mention these, I'm going to mention an application of these that I think the majority of you will already know about. These are diffusion models and autoregressive models. But let's first talk about ancient history 10 years ago. Generative adversarial networks. These were some of the first programs to really get generative data going, right? And again, works by taking 2 neural networks, right, and training them together in an adversarial process. So we have one neural network called a generator that's going to input in noise and output data, and another called a discriminator that is going to input data and output a label of real or fake. They're going to train by trying to make the other one worse. The generator is going to try and trick the discriminator by producing data that it knows from the loss of the discriminator is going to cause it to perform that. And the discriminator has the label of real and fake. It's taking in real samples and the samples from the generator, and it's trying to figure out, okay, which one's real, which one's fake. We're going to train this like a regular old classifier. And as the discriminator improves, its loss function is put into the generator, which in turn is going to try and produce more realistic samples. This process has been sort of compared to the Secret Service and counterfeiters. So the counterfeiters are always trying to produce better fake dollars, and the Secret Service is always trying to develop better techniques at figuring out fakes. Of course, GANs have a lot of shortcomings. Namely, they're very, very difficult to train. We got 3 different problems to talk about. One is the vanishing gradient problem. what happens if that discriminator trains a lot better than the generator? And so now it can always tell when it's dealing with a real or a fake image. And no matter what loss it sends out, the generator just doesn't catch up. That's a vanishing gradient problem. If you see the discriminator loss is constantly going low and the generator accuracy is constantly going low, then you're going to have to rewrite your discriminator to perform a little bit worse. The second is mode collapse. And that's where the generator figures out, if I generate these like 5 different images, right? Just these 5. I can trick the discriminator 100% of the time. But unfortunately, that's not what we wanted. We wanted to match a ton of images within the same statistical distribution and not just like 5 or 10 of them, right? So we're not getting the diversity that we want. And finally, there's failure to converge. So there's no equilibrium reached between generator and discriminator, and so we just don't get good performance from either. Some of these problems we're able to fix using customized loss functions. So mode collapse has been effectively fixed with the Wasserstein GAN. So that is a GAN that is trained with a custom loss function that's the Earth universe distance, I believe, also known as the Wasserstein loss. There are also other generative models we can use than GANs. We've had a lot more since then. Next, we have variational autoencoders. These are released around the same time as GANs, and they are built to work very similar to an older type of generative model called an autoencoder, but it's the training process that's different. The neural networks that we produce are exactly the same. So we have a neural network called an encoder and a neural network called a decoder. The encoder will take in some real data and produce a sort of latent representation. It's the noise that the decoder can use to reverse. Interesting fact, by the way, GANs also have a variant that works like an encoder and decoder called a bidirectional GAN. So you can then have a encoder for the generator. Here, though, if we can train an encoder to perfectly represent a data set, then we can input noise, random noise, into the decoder and get out new samples of that data set. That should be statistically similar to what we had encoded. Compared to traditional autoencoders, there's an extra step added to the decoding process. But otherwise, it's the same general algorithm. That said, it does not have the mode collapse problem that GANs tend to have as often. That said, it does have some shortcomings as well. When tasked with image generation, variational autoencoders tend to produce a bit more blurry results. So here we've got the MNIST data set. So that's handwritten digits, 0 through 9, right? And the one on the right is a lot more blurry. You can still make out what these are, but they're not crisp. There's also a lot less published research on this topic. And I will note, I have given a talk to CySER with this exact same slide before. And when I gave that presentation, I had found that there were 34,000 Google Scholar results for PAEs and 124,000 for GANs. And now it's 64,000 for PAEs and 285,000 for GANs. So they've both gone up, but and with GANs, it's a little bit more than double, and with VAEs, it's a little bit less than double. They're also a bit more difficult to implement, though at the very least training is not as much of a pain. But that's the old stuff. Let's talk about diffusion models. Show of hands, how many of you have ever seen AI art? A lot of the AI art you've seen in the past 1 or 2 years has been produced by an application called Stable Diffusion. This is a diffusion model, it's literally in the name. And the process it's using is called denoising. So what we have up at the right is a couple of images that are being generated using this diffusion process. So on the very right side of this, right, we'll see the properly generated image. And as we progress towards the left of it, right, they'll start to get a little bit more staticky, right? Because the process of learning with a diffusion model is to progressively add noise, right? And then learn the process to remove the noise to get the original picture back. And eventually, we get to a point where we're able to have 100% static. And then we're going to take that static, we're going to take brand new noise, and we're going to get something that's statistically similar to the images we've trained on. Simple enough. I think you had your hand up. Or are you asking a question? No? Okay. So these so far are pretty great for image generation. We don't have a lot of applications of them elsewhere, but I think research in the next few years is going to change that. Then we have autoregressive models. These are also known as large language models. How many of you have worked with ChatGPT? There are a number of hands as well. Okay, so autoregressive models are a feed-forward neural network. So what this means is that we are taking the previous input and output and feeding them into the next input effectively. So we have different types of models for generating sequential data in machine learning, right? And things like RNNs or LSTMs like to embed a memory unit somewhere into the model. And an autoregressive model doesn't do that. Instead, it just takes the last several inputs and outputs and feeds them into the next input to figure out what the next output should be. These autoregressive models are a component, but not the only component, in AI models like generative pre-trained transformers, also known as GPT. Any questions thus far? These are the 4 types of generative models that I've been seeing primarily in my research. No? Okay, so how can we take these generative models and use them for the betterment of cybersecurity? Well, first one I talked about a little bit before, and that's improving data set quality and improving the diversity of data sets. However, we also have a second application, which is evaluating the performance of our cyber defenses. And finally, one interesting application that I found while doing a survey paper on this is that generative models can be used as intrusion detection systems themselves, which is a little bit weird because generative models are supposed to be doing classification in reverse, and intrusion detection systems are pure classification. But let's talk about how we can do these things, right? So how do we improve data sets? Well, our main problem is that we want to be able to train or test an intrusion detection system or some other machine learning application on security data. And that data is unbalanced, right? So let's say we have 95% benign data and 5% of various attack data. So we train our generative models on the minority classes, and we use that to generate more of the minority classes, right? Now, one of the big limitations here is that you can't create something from nothing, so we still have to have some labeled data, right? It would be sort of a dream goal that we could completely eliminate the human out of the loop and just create cyber attacks from nothing, but we can't. So we need some initial data, but we can significantly reduce the amount of human labor that is needed to produce the attack data. And once we've done that, we have a data set that is much better, much more diverse for an intrusion detection system to train on. And that might even allow it to have the ability to deal with some different types of unforeseen attacks. And of course, since we can deal with unforeseen attacks, well, that means that we can also use that to evaluate the performance of our cyber defenses, right? So one of the biggest threats for IDS is going to be zero-day attacks. Well, generative model, we can create zero-day attacks all day long. So we can say, okay, how does our model perform if our attacker has access to the model and can create minor little changes in order to cause it to misclassify? There is a good example of this sort of minor little changes thing, which is when Google was developing self-driving cars, people figured out that you could trick it into thinking that a stop sign is like a 70-mile-an-hour sign by adding little pieces of electric tape or whatnot onto the sign that a human would think is just random bits of tape. It's not like numbers or anything. But the classifier here, it's reading that completely different because it's extremely sensitive. It's not necessarily perfectly able to distinguish out like what the 7 looks like or whatnot. It could think that when laid upon that red octagon, that just the right positioning of like one vertical and one diagonal piece of tape is going to suddenly magically turn it into something else. And if you have something that's that sensitive in an IDS, it could be tricked into thinking that some piece of attack data is benign, especially if you're trying to make your IDS have as few false positives as possible. You might make it more likely to lean towards not an attack than an attack. You don't want to be dealing with all the false alarms. Yeah, our generative models are capable of creating attacks that our IDSs have never seen before. And so we can be using this to figure out what's the best way to improve our IDS. And also, this is slightly different than the task of automated red teaming, where we're actually sort of planning out the stages of an attack. In this case, we're just giving it more examples. Now, with regards to this type of application, there is something I have a bit of concern about, and that is, can our adversaries use generative AI for offensive purposes, right? I know a lot of you are familiar with ChatGPT. Some of you may not have been familiar with this. There have been cases in the past of people trying to create malware in ChatGPT. Now, mind you, ChatGPT is very, very bad at this task. Like, it's not very good at creating programs, but it can sort of do it. but it's getting better over the years. And moreover, even though there are attempts to get ChatGPT to not accept certain types of input, something they call alignment, right? Where they'll get you say, sorry, as an AI model, I can't, and then give you this moralistic spiel, right? It's not going to be the only game in town. GPT-3 is open source. GPT-4 isn't, but there have been countless open source chatbots being made, even by people who don't have access to as much data as the folks at OpenAI. But I think with these kinds of models, an adversary like, say, the Chinese Communist Party might be able to do a little bit more because they are a surveillance state and they have access to more data than we could ever dream of. And so they could use this to create their own AI weapons. So I'm thinking 5 or 10 years down the line from now, let's see what they're up to. A good IDS might be able to counter a good AI-based attack. And it might not have to worry as much about false alarms if, say, 5% of your network traffic is automated cyber attacks, because then a 1% false alarm rate is, relatively not as bad. Although then you still have to have a ton of people to respond to those actual threats. But that's what incident response is for. So that's my concern. But let's look on the brighter side also. Generative machine learning models as IDSs. Both GANs and VAEs train 2 neural networks. And at least one of those is a classifier in both cases, right? Well, with GANs, I found in my research that there are cases of using it as a IDS, and that is to use the discriminator as a classifier. And the generator is providing novel attack data as it's being trained. And for VAEs, what they're doing is they're using both the encoder and decoder to learn a data set of benign data, and then you take in all of your real data coming in, right? And you can use the reconstruction loss from the decoder as an anomaly detector. So if it's trying to reconstruct something that wasn't in the initial data set, it's going to, have difficulty producing the same flow of information, right? And based on my research, I found that a lot of these models actually perform better than traditional IDSs, perhaps because they are trained in a sort of adversarial environment. They can deal with attacks that normal IDSs don't have. That said, other than GAN for VAEs, I have not found significant amounts of research using other types of generative models. I have found exactly one preprint of a paper using a diffusion model as an IDS and nothing else. So I'm hoping we're going to see more research seeing, well, how are our new generative models functioning for these tasks? Finally, I've got some other work that's not generative models, but that is dealing with a number of the data-related problems associated with IDSs. And this is called Tomato, or Threat Observability and Monitoring Assessment Tool. And this is dealing with the problem of we have too many different types of cybersecurity data. So I mentioned before that a host-based system might be able to collect information on like process information, when the driver loaded or unloaded, or network information, and so on. And if you're collecting all of this information, then finding a cyber attack is going to be like finding a needle in a haystack. So we need to be able to figure out of this, what all is relevant. And Tomato is sort of a metric for this relevance that measures what we call observability. And what it does, in effect, is it considers all of the benign traffic going on some host or some network. And it says, what is the likelihood that a cyber attack is going to be mistaken for our benign traffic? And would we be able to find it at all using this particular method of collecting information, right? So that's Tomato. That's something I've been working on with a few undergrads here. So I'm curious, do we have any questions thus far? Yes. That's the end of my presentation. Yes.
I got a quick one. What are some of the, I guess, tangible consequences of a false alarm, like a false?
I would say the biggest consequence is that you're going to waste people's time. So you are either going to have two things coming out of false alarms. One is that all alarms are ignored because you've come to expect that if you hear an alarm, it's more likely that nothing is responsible for that, right? If 80% of alarms are false, you can safely ignore most of them, right? But say you're a bit more diligent, right? You've hired, say, 5 or 10 people just to deal with all of these alarms every single time. That's a lot of money down the drain just to deal with nothing burgers day in and day out. And even still, they might still be trained to default to thinking there's nothing wrong here because, again, 80% of them or 90% of them are nothing. So you might look over details because, hey, I've got to go get to my lunch break. I don't want to deal with this crap right now. So yeah, false alarms basically weaken our confidence in its ability to function at all.
One thing you have to consider along with that though, when you're talking about the cost of a false negative, a false positive, you have to also consider the cost of a false negative too. So
yeah,
cyber attacks getting through that are not identified, those are going to have a large cost associated with them. So
yeah.
It's kind of you got to find it on the balance.
Yeah.
Just make sure I haven't confused this. So you're saying we're going to run like two different models, one that's the distributor and one that's the generator. Is the generator making noise that's meant to look like normal data or like text?
The generator is a machine learning model that the input is noise, right? So you read a bunch of bytes out of whatever random device is on your machine, you put it into the generator as a feature vector, and the output of it is an image or a feature vector or whatnot. It works as any other generative model, right? It's trying to learn to create good quality feature vectors from noise. And the thing it's using to regulate its ability to generate good data is the loss of the discriminator, right? So loss is sort of your metric for how good or bad it is, right? So the discriminator, if the discriminator is incorrectly predicting more of the feature vectors produced by the generator, right? Then that's good for the generator. If it's correctly predicting it, then the generator is going to have to use that loss to say, okay, we're going to alter our neural network structure, our weights, et cetera, to try something different.
Working on like trial and error. Is
Yes, that's kind of how a lot of machine learning models are working. So they're using some sort of a loss function until they get it right. Usually you'll start out by randomizing the weights of the neural network and then tuning them and refining them to maximize some sort of, or sorry, minimize that loss function. Any other questions?
Just a side note for the WSU students, if you're interested in learning more about neural networks, there's a really good course, I think it's 434, called Neural Network Design and Application. So they talk about JNs and all different kinds of neural networks and that kind of stuff.
I would also recommend any of the classes offered by that are older on AI, because those are very much fun, and you'll learn a little bit of you'll learn about different types of classifiers, but you'll also learn about like planning problems for AI. All right. Any other questions, or are we good? I have not paid attention to time at all. It's 10:29.
Perfect time. All right.